Alright, week 31, part 2, we're talking about electrical circuits. So, first I'd like you to think a little bit. How do we use electricity? So right here, if you could imagine that you woke up this morning and there was no electricity, right? The electricity didn't exist, not like the power's out and you're going to use battery operated stuff, but electricity did not exist. So I'd like you to list sort of from the time you wake up, three things that would be radically different right here if electricity did not exist. For example, I went to turn on the lights and there were no lights. Okay, so list three things there just to get you thinking about how often and frequently we use electricity in our everyday existence. The next part of our notes is asking about electricity is so useful because. So here's some words first, I suppose. And the words say energy is easily, or electricity, electrical energy, sorry, is easily stored, transported, converted to mechanical energy. Imagine having to light a coal fire to power up your cell phone. So we use different energy sources. You put gas in your car, for example. There are electric cars, but it turns out that the batteries end up being heavy or whatever. And so when you're talking about energy per weight, gas is very effective. But when we really look at electrical energy, it is easily stored in the form of batteries, transported like power lines, and converted to mechanical energy. So when we talk about electrical energy being converted to mechanical energy, here's an example. So, a hydroelectric plant works like this. So here's a waterfall, and it spins the wheel. And there's an old one of these if you're headed up towards Snow Creek. If you're on the bike path, you can see one. And so this rotates something which we'd call a generator. And a generator is actually just like an electrical motor. And we have these in class, and we'll be working with them. So you get something turning something, and it creates electricity, and that flows through the motor, and the motor can then be used to pick something up, to do mechanical work. The sort of flow chart here says potential energy of water via the generator is turned into electrical energy. There's some energy lost due to heat, so this will never be perfect. If there were 100 joules of potential energy here, you're not going to get 100 joules of useful work out. You'd get something less than that because of this energy lost to heat. The electrical energy then goes through the motor and turns into work done by motor. So this would be useful mechanical energy. Useful mechanical energy. And a lot of the time that is what we are using electrical energy for. Okay, so just a little example there. When we talk about conservation of charge, so here's a simple circuit. We have a power source here, so let's just call this a battery, because we'll be using batteries and light bulbs in class. This is a light bulb. And again, a lot of the energy, electrical energy we use is to turn lights on inside so it's not dark. So if we were to draw, this is of course not drawn to scale, if we were to draw electrons, the electrons would look something like this. Notice how they are evenly spaced. Okay, it's a common misconception that, so within artistic license, notice how they're evenly spaced. It's a common misconception that the battery is pushing on the electrons, so pushing on the electrons that they bunch up right here, right before they pass through the light bulb. Because electrons can flow easily through the wire, there's basically no resistance, and then when they get to the light bulb there is some resistance, and it's that pushing of the electrons through the light bulb that actually creates the light energy, or turns electrical energy into light energy. So the battery pushes, and the light bulb, as the electrons move through it, the electrical energy is converted to light energy. But notice how the electrons are evenly spaced. And so we'll have some computer simulations so you can see this, but if I were to make these electrons move, they would all be moving at the same rate. And the rate at which the electrons are moving we call current. So current. And I think this has been mentioned before, but the reality is that the electrons move. Okay, this is the reality of what happens, but scientists, before the understanding of what actually happened, defined this to be current. So we call this conventional current. So conventional current actually flows from positive to negative. That's just by definition. So here's the positive end of the battery, the negative end of the battery. Remember, the long side is the positive, short side is the negative. So we say conventional current goes this way, even though we know that the things that are flowing are actually the electrons flowing through the metal going in the opposite direction. Sorry that that's confusing, but that's the way it is. Okay. So one more thing about this when we're talking about conservation of charge. So the electrons, they don't get used up in the light bulb. They don't bunch up. They stay evenly spaced. They move through the light bulb. And the electron or proton, we call it the fundamental unit of charge. And so the charge on the electron, we learned this a couple weeks ago, is 1.6 times 10 to the negative 19 coulombs. So this would be good to know. That is a charge on the electron or proton. You know the electron's negative, proton's positive. Electron and proton. Fundamental unit of charge. You'll never find half an electron. Well, at least you hope not. Okay. Here are some formulas. Just most of these are review. We have talked about this, but I'm going to label all these variables. So voltage. Voltage we learned is energy per charge. So just rearranging this formula would make it look like this. Again, we use Q for charge and E for energy. And always good to review units. So energy is measured in joules, voltage is measured in volts, and charge is measured in coulombs. Okay. I, what does that stand for? Yes. Current. And that's current is charge per time. And if we were to talk about units for these guys, current measured in amps. You can abbreviate that capital A, or you can actually write amps. Charge, again, is coulombs, and time measured in seconds. Okay, and then down here we have power. We've definitely talked when we were talking about kinetic and potential energy. So power is energy or work per time. So energy per time. And power is measured in watts. Remember, watts my power output. Haha. Energy, joules, time, seconds. And so these all kind of come together to give us this. This is new. When we're talking about the power dissipated or used or produced in an electrical circuit. So we can say power is current times voltage. Current times voltage. And because the units for all of these are listed up here, I'm not going to rewrite them here, but you might want to. Okay. So those are some formulas. Now circuit diagrams, well, lots of information here. So circuit diagrams, just write in what these each are, and I'm going to show you over here. So power or power source or battery, resistor, light bulb, wire, voltmeter. Voltmeter, ammeter. So voltmeter, I'll write this in here, measures, yeah, you guessed it, measures volts. And I'm just going to write this in so that you have it. And we'll talk more about what that actually means next week. But have that in your notes and it will be helpful. An ammeter measures amps, which is current. And this, we're going to say, is placed in series in the circuit. And you'll learn eventually what that means. And then switch, capacitor, and ground. So here we go. Let's see. Ooh, that's weird. Alright, so conductor or wire is just a straight line. A switch looks like this. You imagine this thing being closed. If the switch is closed, then current can actually flow. Fuse, we will talk about these, but you don't have to really know the symbol. But a capacitor, definitely write this down. Inductor, we will play with these. We have them in class, but we won't get all mathematical with them. Potentiometer is a variable resistor. If the arrow were in a different location, it indicates different resistance, but we'll definitely be dealing with resistors, so these are the squiggles. So these are the important ones: resistor, wire, switch, capacitor. Definitely have those written down. And, oh, cool, let's see. Battery, sometimes just two little lines, sometimes more, that's fine. Ground, yeah, and then a lamp or light bulb. Make sure this is listed. Generator, voltmeter, and ammeter. So V and A, pretty straightforward. Make sure you have those symbols down, and we will be drawing some circuit diagrams here soon. Alright, so here's just this is more of a picture. This is not a circuit diagram. This is a picture of a simple circuit. So what we have is a battery, and a car battery looks just like this. Notice how there's red, the positive terminal, and then black, or blue in this case, for negative terminal. And this is showing that so the little arrows indicate the direction of the current. This would be the conventional current, right? Even though we know electrons are going this way, we say conventional current goes from positive to negative. So definitely have this written, conventional current. And it looks like some work was being shown here to solve for the current. We know that the voltage of the battery is 12 volts, and the resistance of this light bulb is 3 ohms. That's that guy right there. So the current that would flow if we solve was 4 amps. And what we are shown here, this is an ammeter. And so the current has to pass through it. That's what's meant by series. And we'll get to that. So you should know that that's ammeter. The current is 4 amps in this situation. Resistance of the light bulb is 3 ohms, etc. Okay, so drawing those gets to be kind of tedious. So here's the actual circuit, and then the circuit diagram that relates to that. So we have this situation. It's still the battery, and it goes through the 3 ohm light bulb, and then the current comes back. So to measure the current, we would pass the current through an ammeter. So that's this drawn into the circuit diagram. The light bulb looks like this, and sometimes you can even just draw a light bulb like this, as in a resistor. And notice how this voltmeter, when the wires are connected towards the ends, or at the ends of the light bulb, we say this is placed in parallel, and we'll talk about that. But anyway, this is a circuit diagram for this situation, so we will get practice with that. Okay, and again, positive, negative, long side, short side. So let's solve a couple questions. These are just using our simple formulas. We have it's basically either this, the PIV, power equals current times voltage, or Ohm's law, voltage equals current times resistance, or some variation of those. The current through a light bulb was connected across the terminals of a 125 volt outlet. The current through a light bulb connected across the terminals of a 125 volt outlet is 0.5 amps. Okay. At what rate does the bulb convert electrical energy to light? So at what rate does the light bulb convert electrical energy to light? The rate of energy conversion, energy per time, is power. So the question is asking us for power. We know voltage and we know current. This is what it would look like in real life. This is an actual circuit diagram. So this represents this. This is easier to draw. And we would just plug into power is current times voltage. So we have 0.5, 125. Again, this is measured in amps. This is measured in volts. Power is measured in watts. So you could say W, or you could say watts. All right. Second example. A flashlight bulb is rated at 0.9 watts. If the light bulb drops 3 volts, how much current goes through it? So voltage drop means how much voltage is used up. So the battery provides a push, moving the electrons through the circuit, and some of that is used up. We say the voltage has dropped. So voltage drop just means voltage used up. So we have power, we have a measure of voltage, and we're looking for current, plug it in. You get to this point, it looks pretty simple, and we divide, we get 0.3 amps. And that would be a measure of current. Okay. Third example, 75 watt light bulb, is connected to 125 volts. Draw a circuit diagram. What is the current through the lamp, and what is the resistance of the lamp? So, here's a circuit diagram. We got a power source, our battery, and wire, and then our light bulb. Question tells us the light bulb is a 75 watt bulb, which is pretty bright, not super bright. 125 volts, like a wall socket. After substituting into power equals current times the voltage. Power measured in watts, voltage measured in volts, we can get 0.6 amps for the current. So that was this, what is the current through the lamp? And then what is the resistance? Here's ohms off voltage equals current times resistance. And so voltage and current, and we solve and get 208.3 ohms for resistance. Okay, a couple examples there of circuits and calculating current, voltage, power, etc.